So, wave function collapse is a thing you can do, I guess. Yeah, welcome back everybody. Before we get started, just make sure you get all the prerequisites downloaded from the description before continuing on with the lesson. Alright, so once you've downloaded and opened the project from the GitHub repository, the first thing you want to do is go up to the project menu, select project settings, go to the plugins, and make sure you enable the wave function collapse plugin. Once you've done that, you'll see a new tab up top called WFC Editor. So let's click that. And in here, you'll see it's just an empty window. So let's populate this with some data. We'll hit the import button and we will select tile set prototype. The first thing this is looking for is the TRES file that represents our tile set. The next thing it's looking for is the JSON file that stores all the rules. And for this particular set, it's going to be proto_rules.json. So let's just open that up. Now you can see we got a bunch of data here. If we look to the left, we have a list of all the tiles that are in the tile set. And you can cycle through these. Let's just go back to the first one. And looking above, to the right, below, and to the left, you can see there's these little wings. And these wings represent what are called adjacency constraints. So you can see that all of the tiles are also listed in these wings and they have toggle options. So if the option is toggled on, that means the tile can exist in that space. And if you look in the center, you'll see a visual representation of what it would look like if you placed the tile there. So you can see all of the ones that are checked off are tiles that would reasonably go there. And if it's not checked off, it's because it wouldn't fit. So you can see if we cycle over some of these options, it doesn't really make sense to put that tile there in that position. And it works exactly the same way as you go around. So to the left, you would have these options, and below, it's the same the whole way around. And if we look in the bottom left, you'll see there's this number called frequency. And that is what defines the frequency constraints. And the frequency constraints in wave function collapse refer to how often should a tile appear in our tile map. So if we look at this solid blue tile, we can see that it has a frequency of 146. And all that means is that of all the tiles from the input data set, this one occurred 146 times. And if you go down through, you'll see that they're all a little different. So corners appear less frequently, obviously. Walls, everything is here, and it all has frequency and adjacency constraints associated with it. All right, so now that we know what frequency and adjacency constraints are, let's just take a quick look at how the algorithm is going to use that information to populate the tile map. The first step is to observe the map and find the cell with the lowest entropy. Entropy in the context of wave function collapse is calculated as a function of how many options are available to a cell, as well as how frequently those options occur in the input data set. When the tile map is blank, all cells have all options available to them and are considered to have equal entropy. So the algorithm simply selects a cell at random and proceeds to the next step, which is to collapse the cell. Collapsing a cell involves randomly selecting one of the available options using a calculation that considers their frequency constraints. This applies a sort of weighting to our selection process that will favor certain tiles over others, and we'll talk more about that when we get into the code. The third and final step is to propagate this collapse outwards to the cardinal neighbors of the affected cell. This means that we are going to remove from these cells any options that would violate the adjacency constraints of the collapse. The algorithm will continue observing, collapsing, and propagating until either all the cells are collapsed successfully or a contradiction is encountered. A contradiction occurs when all options are removed from a cell. This means that the cell cannot be collapsed and the algorithm has failed. This is something that cannot be entirely avoided, so we will have to account for this in our implementation. Alright, so hopefully we all now have a better understanding of how the algorithm works and kind of how this system's going to function. Let's get back into Godot. and start looking at some scripts. Now, if we go into the add-ons wave function collapse folder here, you'll see there's 3 scripts. And we're not going to be talking about the contents of these files in the lesson because it's kind of out of scope. The WFC editor script is just for the custom tooling, and this isn't a lesson about custom tooling. And the WFC core script does have a lot of useful information in it, and I do recommend that you look at it if you're interested in learning more about how this system works. But we're not going to be covering the information in there in this lesson. The first file that we're going to open up is going to be the WFCCell script and the WFCGrid script as well. We may as well open both of them because we're going to be working on both of them. All right, so getting into the WFCCell class, let's just start filling in some of these methods and have a little conversation about them. This first method, pre-calculate frequencies, is just going to pre-cache some values for us so that we don't have to keep doing the math while we're trying to generate the tile map. And this isn't something that's strictly necessary, but it definitely improves the performance of the algorithm if you do things this way. All right, so the first thing that we do is iterate through the array of raw frequencies, and we're going to calculate the base 2 log of those raw frequencies and pass that into another array. The next thing is going to be calculating the sum of the raw frequencies, and then we just set the sum of the possible frequencies to that same number, because if you remember from the beginning of the lesson, at the beginning of the algorithm, all tiles are possible in any cell, so we can just use that same number. And lastly, we have to iterate through the raw frequencies once more and calculate the sum of possible frequency log frequencies, which is a number that we use in our entropy calculation. And on to the remove option method. The first thing we're going to do in here is just set the option at that index to false. And then we're going to recalculate our sums. So sum of possible frequencies will just subtract the raw frequency at that index. And the sum of possible frequency log frequencies, we will subtract the log frequency at that index. All right, and moving down to the entropy calculation, let's just quickly fill this in. Now, this calculation has to account for the frequency as well as the number of remaining options. And at the end, you can see we've added this entropy noise. That's just a very small random value that's generated when a cell is instantiated. And what that does is it makes it so that there will always be a single cell that has the lowest entropy. Before we start filling out the weighted random index method, let's go ahead and try to visualize what this method actually has to do. All right, so it isn't enough to just grab a random option from the array as long as it's valid. That doesn't account for the frequency with which these tiles should actually appear in the map. So the way that we have to do this is first, generate a random number between 0 and the sum of possible frequencies. And then we're going to iterate over the options array. And when a valid option is found, we add the frequency of that option to the pointer. And then we check if the pointer value is equal to or greater than the random number. If not, we resume iteration of the options array, else return the current index from the options array iterator. So let's just go through this and visualize how this is actually going to play out. So first we get our random number, and then we iterate through the array. And 2 is a valid option, so we've added the frequency of 2 to our pointer value. You can see that it's still less than our random number, so we're going to continue iterating through the options array. 4 is valid, so we've added that frequency, and back to iteration. And there we go. We have found our value of 7. So the index of the tile that's going to be returned is 7. So knowing that, the first thing we're going to do is just declare a variable for this pointer. And then we're going to generate that random number. And like I said, this will be between 0 and the sum of the possible frequencies. And you'll see that I use WFCGrid.random, and this is just a static random number generator so that we don't have to use a different random number generator for every cell. And now we're going to go ahead and loop through that options array. And we'll say that if the option is true, or false rather, we just continue. And if it's true, we add that raw frequency at the same index to our pointer. And now we're going to do that check to see if it's greater than or equal to. And if it is, we'll return that index. If after we've iterated through the entire options array, we still haven't located an index to return, we'll just return -1. And that's how we're going to signal to the rest of our code that a contradiction has been encountered. And getting down to the last method here, this is where we're going to collapse the cell. So the first thing we're going to do is we're going to get that weighted random index. Then we're going to set our tile index for the cell to that weighted random index. Then we're going to say that the cell is now collapsed. And then we'll just iterate over all of the options, and we will set every option except for the one that's been selected to false. And lastly, we just want to make sure that we return the weighted random index instead of -1. And with that out of the way, let's just go ahead and hop right into the WFCGrid class. Hopefully these method names look familiar to you from the beginning of the lesson. Let's go ahead and fill out the observe method first. First thing we're going to do here is we're going to check if that entropy grid is not empty. The entropy heap rather. And if it's not, we're going to pop some coordinates out of it. And the next thing we're going to do is check if the cell that corresponds to those coordinates has already been collapsed. If it hasn't been collapsed, then we will return those coordinates. And if everything in the heap has been collapsed, we'll just return entropy coordinates.invalid. The code should never reach this point, but if it does, it gives us another way to know that the wave function collapse is complete or invalid. All right, and moving down into the collapse method, the first thing we want to do is get the index that we're trying to collapse to. And we can use the collapse method from the cell to do that because it returns an integer. And the integer that it returns actually represents the tile index that we're collapsing to. And the next thing we're going to do is add those coordinates to the animation coordinates queue. This algorithm executes too fast to be animated in real time. And then we're going to push a new removal update to the removal update stack. And that just consists of the coordinates for the removal update as well as the collapsed index. And this is how we're going to communicate to the other tiles which options need to be removed from them. And lastly, we will just subtract 1 from the remaining uncollapsed cells. All right, and moving down into the propagate method, the first thing we're going to do is go through our removal update stack. So while the count of that is greater than 0, we are going to grab that removal update at the top of the stack. And then we're going to check the tile index of that update. If you remember from the other parts of the code, we said that if we set the tile index to -1, we knew that the collapse was invalid. So we'll set valid collapse equal to false and simply return here. The next thing we're going to do is get an array that represents the cardinal directions relative to this cell. We can just do that with coordinates.cardinals. And we'll open up a for loop to go through our directions. We'll say int d for direction. We're going to get the length of the adjacency rules array at the dimension of 1. And we'll just use the d value to get the cardinal for that direction. And these are organized up, right, down, and left. So as we iterate through, that's the sequence that we will see them in. And now we're going to check whether or not we should wrap the tile map. And wrapping adds periodicity to the map. So the tiles on the right and top will match with the tiles on the left and bottom. And if we're not wrapping, we want to check if it's in bounds. If it's not in bounds, we'll just continue. We don't want to do anything there. And the next thing is going to be getting a reference to the current cell, which will be the cell at the current coordinates. And then we're just going to check if that cell is collapsed, and if it is, we'll continue. We don't want to do anything else. And then we're going to go through our options. So we'll just create another for loop for that. And this is going to be get length at dimension 2. And next we're going to check if that option within the adjacency rules is set to false, while the option on the current cell is set to true. And if it is, we're going to make the option on the current cell false. And we're just going to do that by using our remove option method. If we don't use the remove option method, we're not going to be updating our frequency sums, which is going to affect the way that the entropy gets calculated. Since we removed options from that cell, that means that the entropy is going to be changed. So we're just going to add those coordinates to the entropy heap so that during the next iteration of the algorithm, it will get processed. And that's going to be all we need for the propagation method. All right, and moving down into the last method here, the first thing that we're going to do is call a method called reset and pass in a value of true. And then we're going to say that busy is also equal to true. And then we're going to create a new stopwatch so that we can actually measure the performance of the algorithm. And then we're going to set up a for loop so that we can keep track of our current attempt versus our maximum number of allowed attempts. And in here, we will just add 1 to the current attempt. We will get a random cell, so we have something to seed our collapse with. And then we'll go ahead and add that cell coordinates to the entropy heap. Now we're just going to say while our remaining uncollapsed cells is greater than 0, we're just going to go through our observe collapse propagate loop until it is equal to 0 or less than 0. And we're just going to check if the collapse is valid and I is less than max attempts. We're going to try again. max attempts -1 rather. And we'll just reset, but we won't pass in true this time because we want to track the current attempt. Let's also check on line 67 if the collapse is valid as well. And we'll stop the timer. And we'll create a new WFC result. And this is used for a callback to inform any code that's accessing this class that the wave function collapse is completed. And it will also tell the code that it was completed successfully or it ran into a contradiction failure. And the last thing we're going to do in here is invoke a callback. And this is the callback that you will receive this result from. So if you're trying to interact with this from a custom script outside, you're going to want to hook into that callback so that you can get this information. And set busy to false. All right, so hopping back over to Godot, let's just go ahead and open up the proto test scene. So that's going to be right here. And once you're in there, just click on the node 2D in the scene hierarchy and make sure that the test.cs script is attached. If it is, come up here and make sure that your width and height are set to 35 and that the rule path is correct as well. And we're going to want to use that proto-rules.json file. So if it's not correct, drag that from the file system up into the rule path box and it should update it. And you can leave wrap on or turn it off for this test. It doesn't really matter. So now we've got it open. We just have to press spacebar to generate our map. And you can see that the map is generated in the animated way. And this is controlled by that test.cs script. We're not going to cover that, but feel free to have a look at it so you can see how we've achieved that functionality. And let's just have a quick look at the output down here. So we can see that the result was successful. It took 38 attempts and it took 32 milliseconds to actually generate the map. You can see that the animation took much longer than 32 milliseconds. And if we actually animated this in real time, it would have been finished in 32 milliseconds. So it wouldn't appear as if it was animated at all. Running at 60 frames a second, there is almost 17 milliseconds per frame, right? So that would have taken 2 frames to animate. So let's just close this out and we'll break it on purpose. So we're just going to set our height to something like, say, 150 by 150. And watch what happens when we try to do this. So we'll press spacebar again. And you can see that we have a contradiction failure. It used all 100 attempts and it took 903 milliseconds to do it. Now, this happens because the more information you're trying to process through this algorithm, the more likely it is to fail. So it's very important that you're using a good input data set to try to prevent these contradiction failures. There are several ways that you could get around this. You could add a tile that would fit next to any other tile so that there would always be an option available. But in my opinion, that's not a very good solution. Another solution you could use, instead of regenerating the entire tile map every attempt, you could keep track of all of the changes that you made and just undo a certain number of them so it would cut down on the amount of time it would take to do each iteration of the algorithm. Then you could do more attempts more efficiently. Another thing that you could do to try and address this is to generate the map in chunks. So say it works fine with 25 by 25, but it's not working with 150 by 150. If you break that 150 by 150 up into separate chunks and generate them separately, it's far more likely that every chunk would succeed than trying to generate all of them at once. You would just have to implement some logic to take into account the cells adjacent to the one that you're trying to generate. So by region. So if you were generating a region to the right of the current region, you would want to make sure that the left cells of the region that you're trying to generate would match up with the right cells of the one that's already there. And it's the same for all the directions the whole way around. You would just want to check that so that you could do this in pieces instead. And that would make the algorithm far more likely to succeed. Now you might be wondering, you know, this is great, but these tiles look like crap and you would never use them in a game. So how would you actually implement your own tile set into this? And I've created this system to make that as easy as possible for you. So the first thing that you're going to want to do is create a scene with a tile map in it. And then you can paint that tile map in kind of the style of map that you want to generate. And once you have that template laid out, you just come back into this WFC editor window and you can drag that right onto the tile list. And it will automatically populate all of the frequency and adjacency rules for you. Doing this usually isn't enough. It is going to take some fine tuning because just dropping it in like this, you're still going to get some contradiction failures rather frequently. But if you find that that is a problem, you can just come back into this window and modify these values. So if you see tiles that should exist next to this, you can just go ahead and toggle them on. Or if tiles shouldn't exist, you can toggle them off. And you can also mess with the frequencies. So if you want the tile to appear more frequently, you just change this number. But after you change the number, make sure that you hit this apply button or the changes won't take effect. And once you've done that, once you've set everything up the way that you want it, you just hit this export rules button. And this is going to generate the JSON file for you. So you can just save this as dungeon rules, for example here. And we'll just overwrite it. And that's going to change those rules. And it's just a JSON file where all this information is stored, right? And this keeps track of all the frequency and adjacency rules that you've put in. And you might have to keep tweaking this until everything finally falls into place and works, but I promise it eventually will. The algorithm is only as good as the data that you pass into it, and if you pass it bad data, it's not going to succeed. The other thing that you can do with this system is just create a new one, a blank one from scratch, and you'll have to provide the tile set resource, so you do have to set that up first, but once you have that, you just hit open. And you'll see that everything is blank. There's no frequency, nothing is toggled on for any of these. Or alternatively, you can do what we did at the beginning of the video and just import your tile set and rules. And this is how you would do it if you wanted to, say, exit the program and come back. You're still going to need those rules and that tile set that you generated by just dropping your template map on. And this is how you're going to reload that back into the system. And you can see that all the data gets populated that way. That's pretty much going to wrap it up for this video. I'd be very interested in seeing anything that you guys came up with using this. So if you put this into any of your projects, let me know, and I will definitely check it out. If you found this content helpful in any way, please take the time to like and subscribe. It really helps out the channel a lot, and I really appreciate it. I work pretty hard on this stuff for you guys. So with all that being said, we'll see you next time. Take care.